So we will continue our discussion on eigenvalues and eigenvector. We particularly saw the relationship where A was a n cross n real matrix when multiplied with a vector V. If it is giving you another vector which is just a scaled up version of vector, irrespective of whether the scaling factor is a real or a complex number, then we say label that scaling factor as eigenvalue and the vector as eigenvector. Okay, we also saw that for a given matrix and a given eigenvalue of that matrix, the corresponding eigenvector is not unique, because you take up any scaled version of that vector, the scaled up vector is also eigenvector corresponding to the eigenvalue. Further, we discussed a few examples where we saw how to calculate eigenvalues associated with a matrix, and for that we saw what a characteristic polynomial is and how is that characteristic polynomial associated with the matrix identified. And then we also, through the examples, saw that once we have the eigenvalues in hand, then how can we compute the corresponding eigenvectors. Okay, and towards the end we had left with the question to the audience: are the eigenvectors linearly independent? So given a matrix A, you find the eigenvectors corresponding to all the eigenvalues. Can it be shown that the eigenvectors are linearly independent? Okay, that is what was the final question that we left off. So I am still keeping this question open for the audience to find an answer to, whether it's a yes or a no. So in the examples that we have taken in the lecture prior to this were the cases where the eigenvalues were either real and distinct, or they were complex and were occurring in conjugate pair. In this lecture, we'll take up examples where the eigenvalues may be real or may be complex, but they might not be distinct. Okay. Please remember that since you are considering the real matrices, eigenvalues, if complex, will always occur in conjugate pair. So if a complex eigenvalue is repeated 2 times, then its conjugate will also get repeated 2 times. Okay. Now, so consider a matrix A which is of this form: 2 1 0 2. You can see that the eigenvalue of this matrix are 2 and 2. So the eigenvalue 2 is repeated twice. Okay, what is the corresponding eigenvector for lambda equal to 2? So if you denote the eigenvector as this, we'll say that this is going to be the following structure and this will be in R2. Why I am so confident? Because A is a real matrix and the eigenvalue under consideration is also real. So the V has to be a real vector. So here, if we use the definition of eigenvalue and eigenvector of a matrix, we essentially end up getting something of this form. Now this gives me a set of simultaneous equations which is the following. First is 2a plus b is equal to 2a, and the second is 2b is equal to 2b. The second equation is a trivial equation. It is something like 1 is equal to 1. The first equation here if I solve it, gives me that B has to be equal to 0. So what to see here, from this set of simultaneous equations, we can only conclude about B to be equal to 0. So eigenvector in this case is anything with A being a non-zero real number with the second component of the eigenvector being compulsorily 0. Okay, and as for simplicity, I'll choose A to be equal to 1, thus selecting my eigenvector as 1 0. Okay, now I have two eigenvalues, though they are repeated twice. There are two eigenvalues in this case, so I should have got two eigenvectors as well. What I am getting is just this one eigenvector. When I say one, I mean that it is just having this one structure where only one variable is free to choose. Okay, every other eigenvector that I choose will be lying what I should say in the span of 1 0. Okay, every other eigenvector will belong to basically all the eigenvectors in this case will belong to the span of 1 0, right? So I can just have one vector which will define the entire set of vectors that can be the eigenvector for A, given the relationship AB equal to lambda. Okay, but there are two eigenvalues, so there should have been two eigenvectors. Well, the answer in this case is no. Take up another example. Let's say it is this. Here the eigenvalues are again 2 and 2. So if you notice the matrices, the first matrix, let me label it as A1. Let me label this matrix as A2. A1 and A2 have same eigenvalues. It is eigenvalue 2 which is repeated twice. Now for this eigenvalue, let's say that again this is eigenvector in which is 2 cross 1 or in R2, and if I solve this, I essentially get two simultaneous equations, which is this. So these two equations are essentially trivial equations, which means A and B can be chosen independent to each other, which indicates that one eigenvector that I can choose is by setting A to be 1 and B to be 0, and let me label this as V bar, and another eigenvector that I can choose is by setting A to be 0 and B to be 1. Right. So there are two vectors that we get here which satisfy the relationship. So we have a V bar to be equal to this, and we have a V tilde to be equal to this. Both the vectors are different and both the vectors are corresponding to the eigenvalue 2 in this case. Whereas for A1, even though the eigenvalue is repeated twice, you have only one vector that satisfies the relationship of AV equal to lambda V. Okay. So this indicates that though the eigenvalues are same, there are some something different that is happening because of different matrix structures. Okay, now the number of times an eigenvalue of a matrix is repeated, it is known as the algebraic multiplicity. Number of eigenvectors that correspond to a eigenvalue and satisfy the relationship AV equal to lambda V, where lambda is the eigenvalue and V is the eigenvector, A is the n cross n real matrix. Okay, this is known as the geometric multiplicity of eigenvalue. Rather, instead of an, I should say of the eigenvalue. Similarly, this is also known as the algebraic multiplicity of the eigenvalue. We'll represent this as m I, okay, where I represents the ith distinct eigenvalue, and we'll represent this as mi bar. Okay, so I'll say that I is the ith eigenvalue that is different from other eigenvalues. Okay, I'll put it this way. So essentially, let's say that to clarify what this I stands for, if A is a matrix in, let's say, R 3 cross 3, and the eigenvalues corresponding to A are, let's say, 2, 2 and 1, then in this case mi is going to be 2. M1 is going to be 2. So here I'll label that lambda 1 is 2. So ith eigenvalue is different from others. So this is 2, which is different from 1. So I'll label that as first set of first eigenvalue. Similarly, 1 would be the second eigenvalue. Similarly, for lambda 2 to be 1, the second eigenvalue, the corresponding algebraic multiplicity is 1. Okay. Now to know the geometric multiplicity, we have to know the structure of A. So we have to know the A matrix. So without knowing the A matrix, we cannot comment on exactly what the geometric multiplicity is for these eigenvalues. But you should note this, that given a matrix, the geometric multiplicity of a eigenvalue is less than or equal to the algebraic multiplicity of the eigenvalue, and of course this quantity is going to be greater than 0. If algebraic multiplicity is 1, then this implies that the geometric multiplicity is also 1. The reverse implication is not true. Okay. So all those vectors, we have been calling them eigenvectors if the vector satisfies this relationship. Okay, AV is equal to lambda. We have been calling them eigenvectors. Henceforth, we'll be labeling these vectors as ordinary eigenvectors or OEVs. Okay, OEV, ordinary eigenvector. OEV, ordinary eigenvector. When Mi is, or so Mi bar is basically the number of ordinary eigenvectors corresponding to an eigenvalue of a matrix. Okay, this is with respect to one eigenvalue. Now when this geometric multiplicity is less than the algebraic multiplicity, then is something known as the generalized eigenvectors, or the GEVs that can be found. Okay, number of generalized eigenvector corresponding to an eigenvalue of a matrix is the difference between the algebraic multiplicity and the geometric multiplicity corresponding to the eigenvalue under consideration. How do you find these generalized eigenvectors? By definition, V is a generalized eigenvector if we'll say that this is of grade K if A minus lambda I to the power K. So you multiply A minus lambda I K times and operate it over the vector V, it will be 0. but this will be not 0. Okay, a minus lambda I to the power k multiplied with v gives you a 0 vector, but a minus lambda I to the power k minus 1 will not give you a 0 vector. Okay, this is for k I should put it this way. For k equal to 2, 3 and so on. Okay, so how far you are going to go in depends on the difference between the algebraic multiplicity and the geometric multiplicity of the eigenvalue under consideration. Okay, so let us go back to the example that we had taken a moment earlier, which was this. We had the eigenvalue to be this, and the eigenvector or the ordinary eigenvector is the OE that we got was this. Okay, so I'll label this as V1. Substitute on the other side. Now to calculate the GEV, let be the GEV. By the way, how many GEVs will we have? Here M1 is 2, and from here we get the geometric multiplicity to be 1. So the number of GEVs is going to be M1 minus M1 bar, which is 1. We'll have 1 GEV. Okay, so let that GEV be denoted as 2V lambda equal to 2. And this will have to satisfy this relationship for k equal to 2. Okay, which with the fact that a minus lambda I k minus 1 multiplied by 2v lambda equal to 2 cannot be 0. Fine, fair. So I'll write it like this. I can split the power of a minus lambda I in this form. Right. I can express it like this. Now notice this guy here inside the curly brackets has to be a eigenvector, because this when multiplied by a minus lambda I is going to give me 0, and on top of it the underlying vector has to be a non-zero vector. Okay, so one solution to this generalized eigenvector is that if I take a minus lambda I multiplied by this to be equal to the ordinary eigenvector that I have in hand. Agreed? So this small relationship essentially yields that A acting on this generalized eigenvector is nothing but lambda times the generalized eigenvector plus the ordinary eigenvector. Right. So if we stick to the matrix that we have in hand, which is 2 1 0 2, and I say that A B represents the generalized eigenvector, the variables for the generalized eigenvector. This I can write as 2A 2B because lambda is equal to 2 plus for the ordinary eigenvector I have this. So let's see what are the equations that we get. We have 2A plus B to be equal to 1 plus 2A. And then we have 2B to be equal to 2B. So the last equation is a trivial equation. And the first equation yields that B has to be equal to 1. Okay. So the GV is going to have a structure where A can be any real number, but B compulsorily has to be 1. Now there's an interesting thing that comes up here. For simplicity, I'll choose A to be equal to 0. This gives me the generalized eigenvector to be 0, 1. Right? But what stops me from choosing A to be equal to 1? So can I choose A to be equal to 1? If I choose, yes, I can do that. If I choose A to be equal to 1, then the generalized eigenvector is going to be 1, 1. And you can verify that if A minus lambda I square acts on 1, 1, it gives you 0. Whereas A minus lambda I acting on 1 gives you the eigenvector 1, 0 in hand. The same is true when A is equal to 0. Let's verify this. You have 2, 1, 0, 2 minus of 2, 0, 0, 2. This being multiplied to 0, 1 gives me, this is 0, 1, 0, 0 multiplied with 0, 1, which is going to give me 1, 0. Similarly, if I consider this 1, 1 as the generalized eigenvector, then I again end up with the same ordinary eigenvector, which is 1, 0. So if you notice, irrespective of what the value of A is, I get back my ordinary eigenvector. So until I set the second component of the generalized eigenvector to be 1, I'm fine with any value of A that can go in, or the first component of the generalized eigenvector can be set to any value. So does that mean that we are going to have infinite number of distinct generalized eigenvectors? It looks like so. Okay, but we need only one generalized eigenvector. So which one do you want to pick up? Well, it's a free choice. For me, I am going to pick up the generalized eigenvector to be 0, 1. Possibly this is more convenient. Also, notice that the generalized eigenvector that I have picked up and the corresponding eigenvector that I already have in hand are linearly independent. Okay. So, now when we have two vectors which are linearly independent, we are possibly going towards construction of a basis to represent a space. And as you know that a basis is nothing but a coordinate frame that is going to be set up for the vector space, this is exactly what it is trying to do. The eigenvectors that we find out essentially form the basis for the underlying vector space. And that is where you can actually use or try to, that is why I asked you at the beginning of the lecture to see if all the eigenvectors that you find out for a corresponding matrix, they are linearly independent or not. As we proceed further in this series of lectures and when we encounter linear systems, it will become evident as to what is the importance of the eigenvectors in this particular case and why are these eigenvalues important to know. What are that these two things are going to tell us about the system under consideration. Okay, let us take up another example. Rather, I leave it to you for solving when you have a matrix, let's say of the form 3 1 0 0 0 3 0 and 0 0 1. What are the eigenvalues? The corresponding algebraic and geometric multiplicity, the ordinary and the generalized eigenvectors. To try to find this, you can take another matrix and the same set of questions also follow for this matrix, and do try to compare your answers. So these are two different matrices, hence are two different systems. So one can expect that the algebraic multiplicity, geometric multiplicity might be different. Okay, might be. So I leave this up to you to find out.